Morning all, hope everyone is doing well. I think I've managed to fix the audio technical hitch now, so hopefully we won't have the microphone cutting out again. So I suppose we're looking at part 3 today, final part of Chemistry 1. We need to have a look at the halogens again and finish off the work we did around that. We need to have a look at the noble gases, and we need to move on and have a look at the transition elements. What I'd like to do then is come back and have a look at the reactions between Group 1 and Group 7. Morning Tanishka, morning Amy. Have a look at the reactions between Group 1 and Group 7. And those of you that are interested, I say interested, it needs to come up later on, but those of you that are doing the higher paper, I think towards the end of the lesson we'll also look at how a redox equation fits in with this as well. But we'll start off with, I think we'll start off with the noble gases, and I'm going to put the halogens in towards the end, because that's where some of the more complicated work actually comes in with this one. So last lesson we started looking at the periodic table, and I think what I'll do is the same as I've done with the last couple of lessons. I'm just going to drop the periodic table in here because it makes it much easier to see what's going on. Another one. No, it's not on there. Okay. There we go. So we said that the column number, the group number, tells us the number of electrons in the outer shell. And we said the period number tells us the number of those shells or orbits that we've got. I suppose the other key point we said was that they're grouped based on those number of electrons in the outer shell. And that's what affects the chemistry. That's what affects how it reacts. So Group 1 will have 1 electron, Group 2 will have 2 electrons in the outer shell, 3, and so on. By knowing it, we also said that we can work out the charge they're going to form. So we said that actually the only reason that most elements react is to get to a full outer shell. So Group 1 have 1 electron in the outer shell. So to get to a full, they either have to gain 7 or lose 1. And in terms of the amount of energy required, it's a lot less energy to lose 1 electron than it is to try and gain 7. So for Group 1, they will lose 1 electron to become +1. Group 2 loses 2 electrons to become +2, and so on. What I will do in a minute is I'll have a quick look and see if I can find... I've got a cheat sheet for this one, and I'll drop that onto the Google Drive so that you can have a look at it, because that's got all of these sort of shortcuts that I'm going through now in one place. So you can download that and have a look at it as well, rather than sort of dropping it onto here. Now, we haven't looked at the noble gases first, so I'm going to sort of talk about those first. And like I said, I'm going to come back to the halogens. I know I finished last lesson with it, but because I want to take the halogens and push you guys a little bit further with the information on that. So, when we're looking at the halogens, we are looking at Group 8, or Group 0, depending on which periodic table you've got. That is this group here. Sorry, halogens, the noble gases. We all camped out last night for the part of the scouts. The scouts were trying to beat a world record by trying to get as many people to camp out. So I spent the night in the hammock, and I think the kids and my wife spent the night in the teepee. And I'm quite tired today, so apologies for any mistakes we made. But at least it was dry. So, we've got the noble gases. These all have full outer shells already. So from the point of view of GCSE, they do not react. If you go on and you look at A-levels later on, then actually if we put enough energy into it, and we've got a lot of energy to put in, we can add and remove electrons. But for the sake of GCSE, you just need to put down they don't react. They've got a full outer shell. They're very, very stable. And it would require too much energy to turn them into an ion or to make them react with anything else. Okay, they're found singular. If we compare that to the halogens, as we'll look at later, the halogens are found diatomic, so they're always found in pairs. We don't really ever find them on their own, but these are found singular because they don't need to form a bond with anything because they've got a full outer shell. They're mostly gases, but we can turn around and we can say actually the melting point and the boiling point increases down the group. If we get down to radon, down here, we've got those square brackets. That, again, that generally indicates we've got various isotopes. So we know that these two are going to be radioactive. And if you look at radon, radon is a fairly common gas. It's often formed of a byproduct of the breakdown of uranium. And a lot of granite rocks will have sort of trace amounts of uranium that breaks down. And one of the problems they've had in Cornwall in the past is that the granite rock that a lot of Cornwall was sort of based on, that have formed down there, the uranium, as it decays, has released this radon, and the radon's sort of built up in pockets, and it's been released into the houses, and that's caused sort of lung cancer and some various other issues with that. So when you look at a lot of the houses in Cornwall now, they will actually have ventilation built in underneath the houses, underneath the floor, that rather than it seeping into the house, it sort of dissipates to the atmosphere around the outside where it's harmless. So it is something that needs to be taken into account, but it is still one of the halogen gases. But notice that is a nuclear reaction. That is not a chemical reaction. We're not looking at the electrons themselves being involved. That is the breakdown of the nucleus. So Tanishka, in terms of the elements you have to learn, it's worth familiarising yourself roughly where the elements are, but you don't need to learn any of these at all. That periodic table that I've put up there, that's going to be given to you on the in the exam. So as long as you can get the information off of it, we need to know the properties of sort of the general group 1, group 7 and group 0. We're going to talk about the transition elements today as well, and we need to know some of the reactions, but you don't have to actually memorise any information about specific elements, okay? Because you can just get that straight off the periodic table. Morning, Olivia. So, yeah, in terms of the noble gases, we don't need to know a great deal about it. They got a full outer shell, they're singular, they're gases, and they're very, very unreactive. We still use them, but generally they'll be used in any areas that we don't want reactions to happen. So in some types of welding, we don't want reactions with oxygen. So what they'll do is they'll flood the area with argon. The argon will push out the oxygen, but it means that actually the welding that's going on, there won't be a secondary chemical reaction going on. We know that we use helium. Helium's less dense than air. It causes things to rise up, so we can use it in balloons. And it's also mixed in with some of the deep sea diving equipment as well. When they start diving down into deeper depths, they'll mix in some amount of helium as well. I think I'm right in saying that anyway, with some of the diving equipment. So we've got that. And with a lot of these other ones, neon, krypton and xenon, they're used in some forms of lighting to produce different colours. We've sort of heard of neon lights before, and they can produce quite vivid colours when we're passing electrical currents through. But they're not actually... there's not a chemical reaction happening here. What we're doing is exciting the electrons to higher energy levels, to higher orbits, and then as those electrons drop back down again, the energy they gain has to go somewhere, so it's given out as light. And depending on the type of element, depends on the colour of light. So we generally use them for that because they are unreactive and we're not going to get any sort of secondary reactions happening. So that's pretty much it for the noble gases. We don't really need to know very much because they just don't react. So we can't do a lot with them in terms of chemistry, but we just need to know those general properties. Okay? Melting points and boiling points increasing. So I think I might come back to that a little bit later on because it's slightly more advanced and doesn't really come up why at GCSE, but it's worth covering it. What I'm worried about is we've got other people watching this at the moment. They'll switch off if we go through that now. So I might put that on in the second half of the lesson and come back to it. Right, let's just move this up then. So in the middle, we've got this block of elements here. And these are called transition elements. You don't need to worry too much about electrons and electron configurations here for these elements. Mainly for the fact it comes in at A-level. I'm currently doing some lessons for another company at the moment, and they're doing a lot of work on this one, but it's very, very much in the A-level because we need to go into a little bit more detail about the different types of orbits, the different types of electron configurations, which doesn't come up at GCSE. So we do need to know, though, some of the properties of these. So like groups 1, 2 and 3, they are all metals. they are going to be conductive. They are going to be shiny. So we've got those similarities as well. However, when we start looking at sort of some of the other features about them, some of the other properties, they're also quite dense. Now, we know that group 1 elements, they're not very dense really, because actually they float on water. We put them in, they will float, they'll whiz around. Sodium, we know we put on water, it reacts with the water. It gets hot enough just from the chemical reaction to melt, which is why if we put a cube of sodium into water, it sort of whizzes around and it turns into sort of a round ball. And then, because it's given off hydrogen gas, it will sometimes produce so much energy that it will also ignite that gas. Potassium always ignites the gas because it's even more vigorous, but it's still got a density low enough to actually float on the water. When we start looking at the transition elements, they often become a lot more dense. So actually, if we had a block of most of these and we put them in water, it's going to sink. So we've got the higher density. We've also got a higher strength. So there's a reason why one of the most common structural components for sort of bridges, when we're looking at vehicles, even if we're making things out of concrete, we'll reinforce it, is we'll put iron in, or steel, which is iron mixed with carbon, because actually it is very, very strong. If we look at titanium, titanium is as strong as steel, but it's light as aluminium. So it's an amazing building, and it's also fairly unreactive in terms of when it comes to titanium. So we've got this really, really high strength that you don't get with group 1. And one of the things with the transition elements that you need to be able to do is make those comparisons with other groups. Okay, so particularly with group 1, because you need to know the properties, what are the similarities, what are the differences? They both conduct, they're both shiny. However, if we're looking at the density, we're looking at strength, that is something we don't get a high density, we don't get a high strength with group 1, with any of them at all. We've also got quite a high hardness with them. So we wouldn't look at making a knife out of any of the group 1s. One, because it's too reactive, but also because they're too soft. Whereas with a lot of the transition elements and alloys of the transition elements, so alloys comes up in chemistry 2 when we're mixing metals together, but a lot of the alloys has some sort of really, really quite cool properties, and we make alloy wheels out of them because they're light, because they're very, very strong, it's quite hard. If we mix chromium, iron and carbon together, we get stainless steel. So we get a very, very hard metal that doesn't corrode because the chromium stops it corroding. So we can start getting some quite cool properties out of these, which we wouldn't get from group 1 in any way, shape or form. They're also catalysts. So most of the really common catalysts generally will be found in the transition elements. I mean, the Haber process, which is used quite extensively to make ammonia, developed back in World War II, I think it was, when a lot of the explosives were made out of chicken manure, so chicken feces. It's a massively rich source of ammonia. Now, the problem is, a lot of the fertilisers that were going on the fields to grow crops for food for the soldiers and for the families and for everybody living at home also came from ammonia. So because they wanted to make it increase the amount of explosives during the war as well, they needed another source of ammonia. And there was a German scientist called Fritz Haber, and he came up with this Haber process. Now, I'm not going to go through the chemistry now, because that comes up in a later unit. But he tried a few thousand different compounds, different elements, different molecules, before he came back and found out that the best catalyst for him for this particular process was plain iron. Platinum is also used a lot as catalysts, as electrodes. So we find the transition elements are incredibly useful. Cobalt, at the moment, we can make all sorts of batteries using cobalt technology. We can also make radioactive fuel cells out of some of the isotopes of it. And I think I've read somewhere that actually it's much cleaner, much safer than uranium and plutonium. But because of the research that's been done into atomic weaponry as well, most of the power stations are actually based on uranium and plutonium because we knew more about it. So there's some quite sort of controversial issues there. Tishka, from Lanthan to Mercury. Okay, so yes, Now, if we look at these ones here, so hafnium, and these elements aren't radioactive in most cases. The lanthanums are radioactive, most of them, not all of them, and the actiniums, they are also, actinides, they're also radioactive, but we don't put them in because it sort of skews the periodic table. Remember that these groups, so going down, even in the transition elements, they're still grouped based on similar chemical properties. And the problem is, there's this sort of group that goes in here that's slightly unique because of how radioactive and everything else they are, that if we put them in here, it sort of forces all of that periodic table out. So we generally put them in underneath on two separate lines, but you won't need to worry about that. If there's anything they need to give you based on those, that will be given additionally in the periodic table. So don't worry too much about the lanthanides and the actinides. These ones here, they're not radioactive. I mean, we can get radioactive isotopes, but the most common isotope is not radioactive. A lot of these we'll find in day-to-day life. Okay, iridium, for instance, can be used in mobile phone screens and in various other bits and pieces as well. We know that platinum and gold is very, very unreactive. And again, we wear those as jewellery quite a lot, so they're not going to be massively radioactive either, although we can make radioactive isotopes. Mercury itself is the only other liquid at room temperature. So room temperature is sort of 25 degrees Celsius. The other one being bromine that we sort of spoke about on Wednesday. So yes, you need to be aware they're there, and we can talk about the chemical properties, but don't worry too much about them. Okay, these ones here are not radioactive. Tungsten is really commonly used to alloy with metals because it makes them incredibly hard. So we'll often make tungsten carbide tips for tools where we need a really, really high hardness, very, very sharp edge, chisels, that sort of thing, but it also makes it quite brittle. Drill tips can also be tungsten carbide. So we've got this idea of our catalysts. Other interesting things about the transition elements that we need to be aware of, they're often colourful. Now, it's the ions, not the metals, that are colourful. Yeah, in a lot of the old filament bulbs, we will often use the metals in there as well. Yeah, well done. The metals themselves are still shiny. They look just like we'd expect a metal to be. However, they can have multiple charges, so they can form multiple different ions. Okay, and that's one metal. For instance, if we look at iron, the common ions of iron is +2 and it's +3, and they'll have slightly different colours accordingly. If we look at the ion of copper, almost everybody who's been in a science lab has used copper sulfate at some point, and it's that deep blue colour. If we look at vanadium, vanadium can have 5 different charges on it commonly. Manganese even more, and most of those will have very different colours to them depending on what the charge is going to be. So we can use these in dyes, we can use it in paints to make different pigments, depending on what the use is going to be. We often associate some of the iron compounds as red, because if you think about the fact that your blood is red because it has one of the ions of iron at the centre of the hemoglobin, which, if you remember from biology 1 and 2, that is the red pigment that's contained in red blood cells. And actually, if we're outside and we see rocks that have like a reddish tinge, that usually means they have iron in them. If we see sort of like a greeny tinge to rocks, that's normally rocks that contain some copper compounds to them. So the transition elements can often be quite pretty because they have all of these different colours, and depending on how we prepare them, those colours can be really, really vivid. But we can't turn around like group 1 and say, oh, that's in group 1, it's going to have a +1 charge. It all depends on how it's reacted and what we do with it. And in an exam, you are not expected to remember the charges. You might be expected to calculate the charge based on information that's given to you. And I'll give you a couple of examples of that. If we look at iron, and we look at these two sort of combinations for iron oxide, Both of these molecules are neutral. So they have a 0 charge. We know that oxygen will have a -2 charge because it's in group 6. And if you need a recap on why it's -2, go back and have a look at the last video after this that we did on Wednesday, because I went through that then. And if you're still not sure, drop me an email or put some questions on here and we can go through that. We should know that oxygen's got 6 electrons in the outer shell, gains 2 electrons to become -2. So if I look here, I've got 1 -2 charge. And I've got 1 charge here that we don't know what it is, but we do know that when we add these two together, my final charge is going to be 0 because it's neutral. So 1 times something equals -2. So therefore the ion has to be +2. 1 times +2 and 1 times -2 equals 0. Okay, if I look at the other iron oxide, in fact, let me just rewrite it here so I've got a little bit more space. I've got 3 times -2. That gives me a -6 charge. Over this side, I've got 2 times something, which must give me a +6 charge, because when I add these two together, I'm going to get 0. So 2 times something equals +6. So 2 times 3. So therefore this ion has a +3 charge to it. Now, we can do some more work on that later on. It is definitely higher tier that. But you should be able to work it out from the compounds. And don't worry about it if you don't get it now. This comes up a lot in future topics. There's topics based on redox, and we'll have a look at redox today as well. But when we look at some of the ions that we're going to be having a look at in chemistry 2, when we look at chemistry 3, 4, it's going to come up a lot, so you're going to get plenty of chance to practice this. And when we're back in school, we can do questions on this. But the more familiar you get now, the easier it'll get. And if you want practice on this, it's really easy just to Google GCSE questions on, and then type in what you want to have a look at. Have a look on YouTube as well and see how other people have explained it. Because remember, I'm explaining it in one way. It's not the only way. It works for some people, but other people might like it slightly differently. But do ask if you want a bit more help with any of that. Okay? Another way that we can show the charge of these in an exam, so I could write iron oxide like that, and I could write iron oxide like that. And they might do that in an exam. This is a common, and it's an international standard. By using the Roman numerals indicate what the positive charge is on that ion. So if you haven't been given the molecular structure, but you are given something like this, they've given you the charge in the brackets in Roman numerals. Okay? So hopefully that sort of makes sense and that's clear, but you should be expected to be able to do that one. It's worth, when you get some time, have a look at the first transition elements. Now, I'm not going to go through exactly why now. Scandium and zinc don't technically class as transition elements. At GCSE, you're not going to get it wrong if you call them transition elements, but they're not technically transition elements. And it's to do with how the electrons, for which electrons get transferred when they form ions. So what I would suggest you do, just so you're aware, a bit more familiar, and there's loads of on the internet on this one, have a look at some of the uses of chromium, manganese, iron, cobalt, nickel, and copper. Okay, and just a bit of research, have a look. You'll be quite surprised at how many of these and some of the other transition elements you actually have in items that you use every single day, but you don't realise that it contains these ions in there at all. The other thing that's worth noting is that these three can form magnets. And they're the only metals that can form magnets naturally. So you do need to know that as well. But that's the transition element, okay? So it's worth just being aware of those. Remember that you need to be able to compare it to group 1. In terms of reactivity, they will react. We know that iron reacts with oxygen to form iron oxide, which is rust. It will react with some water, but it's nowhere near as quick. It's nowhere near as reactive as group 1. Okay? Okay, we might actually finish today a little bit early because I'm going to go on now and have a look at some of the more advanced, some of the redox stuff, some of the reactions between group 1 and group 7. I will start off with the basics of what you need. So don't switch off just yet. It'll be a good recap and a good refresher before we start Chemistry 2 next week. And then I'm going to go on and have a look at some of the slightly more advanced stuff, which we're going to come back to multiple times in these videos, because the more you go over it, hopefully the more comfortable you'll get. But do ask questions if you're not sure. Now, so we started looking at the halogens on Wednesday. It's the last video. We said they're group 7. We said they form -1 charges, and they have 7 electrons in their outer shell. It's worth noting they are all diatomic as elements. So diatomic means there are 2 atoms in a molecule. And we'll look at the structure of those molecules when we do covalent bonding in Chemistry 2. But because they're quite reactive, because they need to gain 1 element, they don't really exist in nature as single atoms like the noble gases do. They will exist as these diatomic molecules floating around, and then they'll react from that diatomic molecule. Okay? So you need to be aware of what this word means. It is a key word. It is one that you need to, it is a definition that you need. We said that in terms of the general properties, we said that the melting point and the boiling point increase down the group. We said that the reactivity decreases down the group. And we said actually the colour changes as well. If we look at fluorine, you won't get a chance to work with fluorine in school. It is way too reactive, way too dangerous, highly toxic. And yeah, it's not something you'll come across in school, and probably not even in college. Maybe if you're looking at chemistry at degree level, then you would. But you can still talk about the properties of it, because actually if you know the trends of the rest of the halogens, then you can sort of translate that and carry that through into fluorine. We know that, so fluorine starts off as a very pale sort of yellowy green. Chlorine is still a green gas. Bromine gets darker again and this sort of yellow reddish brown colour, and then that's also a liquid. And then when we get to iodine, it looks like a grey solid, but it's got quite a low melting point, so it sublimes into a purple gas. So the colours sort of change as well. Now, later on, when we come to, I can't remember which topic it is off the top of my head, we'll look at displacement reactions when we do redox properly. Most of you will have seen the reactivity series, apart from if you're in Group 9, so Group 9, Year 9, you will have seen the reactivity series of metals. And even in Group 9, we cover reactivity series in Years 7 and 8. So you will have seen those, and you'll have done some of the reactions with them. So it's worth noting that the halogens as well will also displace other halogens. So if we have a look at this one, this is an experiment you can do, and it is one we do in school. We have the sort of halogen waters, I suppose we can call these, which is basically a solution of each of these. So chlorine water, bromine water and iodine water. We don't use them very often because all of the halogens are toxic. They're more toxic as we go up the group, but they can be useful. Bromine water, some of you will remember that we can use bromine water to test for that double bond in alkenes. So it is something you have seen before, but probably not using very often, because actually the preparation and the use, there are slightly higher risks with it so we don't get them out as often. What we have over here then is our salt solutions. Now, I've kept it really simple. I've just gone for the potassium halides. So potassium chloride, potassium bromide, potassium iodide. I've used the chemical formula because I think it's good you get familiar with these. But actually, if you are struggling with remembering that one, feel free to write these out as notes using the word equations instead of the symbol equations. The other thing that's worth noting is that when we go from an atom to an ion, the name of the halogen changes. Okay, we've got fluorine, chlorine, bromine, iodine. So these ones all end in INE. When they react and they become an ion, the name changes so it ends in IDE. So chlorine becomes iodide, bromine becomes bromide, iodine becomes iodide. So these ones, we've got a neutral charge, and these ones all have +1. And most of the non-metals, the name does change when it becomes an ion. Metals, the name doesn't change, we just put the word ion after it. So lithium atom becomes a lithium ion, just so we know, but the name doesn't change. But when we're looking at non-metals, like I said, in the case of the halogens, we go from INE to IDE. And that's really quite important when we're writing out the word equations, because you will get it wrong in the exam if you get that bit wrong. Okay, so that's well worth making a note and just having somewhere so that we remember it. Now, if you notice what's going on, we should be able to see that if we did this reaction, adding chlorine water to potassium chloride, we get no reaction. But if we add chlorine water to a potassium bromide solution or a potassium iodide solution, then we actually get a colour change, and I've actually coloured these cells in so that we can see there's a colour change, and it's roughly the sort of right colour for it. And we can also see, looking at this one, that we go from chlorine to bromine and potassium iodide. Now, what's actually happening here, if we draw this out, we've got this sort of chlorine molecule, and we're ending up with a bromine molecule and potassium chloride. So I would have to balance this if I was writing this out. So right, let's just put this down as KBr there. So let's do that the same way around, just so I don't confuse too many people. KBr plus is going to form so we would need to balance that if we were actually writing this out properly. But notice what's happening here is the chlorine is kicking the bromine out and replacing it when it's attached to the potassium. So we're kicking that molecule out, and the iodine is taking its place. So the more reactive halogen is going to end up taking the place of the less reactive halogen in the molecule. Okay? So we call this displacement reactions. Happens in metals, happens in with halogens. So in this case, what we're going to be writing down is that the more reactive halogen displaces the less reactive halogen from the compound. And I'm using that word compound very specifically here. I've chosen that word because remember, the compound is a molecule with two or more different elements. Chlorine itself is a molecule, but it's not a compound. but potassium bromide is a compound and a molecule because it's got two different elements in there. So that helps me help somebody else identify what I'm actually talking about here. When we work our way down the halogens, remember that these become less reactive as we go down. So we're actually getting less reactions happening. Bromine won't displace chlorine or chloride. It's obviously not going to displace itself, but it will displace iodine, iodide from the molecule, because iodine is less reactive. So the more reactive halogen is always going to end up attached to the metal. Now, this is where we get a little bit more advanced. So if you're doing foundation, don't worry about this too much. It's worth having a look. Ask questions if you need to. It comes up much later on, but it's worth me covering it here because the more times you see something, the more likely you are to remember it. So yeah, let's just go through. We're going to have a look at what we call redox. So redox stands for reduction and oxidation. There is an acronym that you need to know. It's one that we come across before. It's not anything new. I learnt it when I was at school, so it's got to be properly old. So, and that is oil rig. So what we're looking at is the oxidation is the loss of electrons let's do this properly, hang on. Getting ahead of myself. There we go. Right. Is loss of electrons. Reduction is gain of electrons. So what I want to do, I want to have a look at what's happening during these displacement reactions, okay? So let's have a look. Let's write one of these out again. Let's just change the colour for a minute, back to black. So we're going to have a look at chlorine plus potassium bromide forming bromine plus potassium chloride. I am going from an molecule. Okay, but this is, these are atoms because they have no charge to them. So it's really important to note, this is neutral. These are ions. Okay, this is an atom, so this is neutral. These are ions, so they're charged. Now, the reason I've put that down is, if you think about it, chlorine, in order to go from a neutral charge to an ion, it must have gained electrons. We know that it's in group 1, so therefore it's going to form a -1 charge. Potassium is, in group 7. Potassium's in group 1, so it forms a +1 charge. If I look over here, potassium's +1, bromine is -1. So the potassium doesn't change charge at all, so we're going to ignore that. So I'm going to put in here potassium is a spectator ion, as the charge does not change. Okay, so we can effectively ignore it when we're looking at electron transfers. Now, let's have a look at what's actually happening. So chlorine, and I'm only going to draw the outer shell here because it's much less confusing for you. So I've got chlorine here. There we go. I'm going to put bromine here. So chlorine has 7 electrons in the outer shell. Chloride has 8 electrons in the outer shell. Bromide has 8 electrons. Bromine has 7 electrons. So what's actually happening here is one of these electrons on the bromine is being transferred to the chlorine. Okay, so Tanishka, potassium's in group 1. So as an atom, it only has 1 electron in the outer shell. So all of group 1 has 1 electron in the outer shell. Now, atoms do undergo chemical reactions to get to a full outer shell. Okay? So, in other words, for potassium to get a full outer shell, it's either got to gain 7 more electrons, or it can lose 1. So, if it loses 1 electron, it's now lost 1 negative charge, which means it's become positive by 1, because it's going to have 1 additional protein compared to the number of electrons. If you're not sure, go back and have a look at chemistry 2, the video 2 to this one, because I covered quite a bit of that there. And then drop me a message if you're still not sure, and I'll go through that. But when you look at group 7 has 7 electrons in the outer shell. So it's going to gain 1 electron to get to 8, which means it's gained a negative charge, so it's got a charge of -1. So we know that all of group 7 form a -1 charge. We know that all of group 1 form a +1 charge, and so on. I will drop the cheat sheet for this into Google Classroom later on. And for anyone else, I'll drop it onto my website once I finish getting that sorted out, so that you can have a look at it there. So what's happening is the bromine here is losing 1 electron to the chlorine. The chlorine's becoming chloride, and the bromide is becoming bromine. Okay? No, not a problem. Tanisha, I'd rather you ask questions when you're not sure about things than just sit there and stew on it, because as we're online at the moment, I can answer the questions a lot more easily in front of the camera. But like I said, if you do have a look at it later on and you're still not sure, drop me a line and I will sort out some resources and some other bits and pieces for you. Okay? We're covering quite a lot of information and quite tricky stuff. So there's loads of bits and pieces to get your head around here. What I'm hoping is that by going through it now and multiple times in future videos as we get to it, we should build up that understanding. And what you'll also find is you'll be looking at things going, oh, this is really hard, my head hurts. But things will start clicking into place and it will start making sense. So this is difficult stuff, but that's absolutely fine, because actually we only get better by pushing ourselves. If we don't make mistakes, if we don't stretch ourselves, if we're not out of our comfort zone, we never ever make the progress we would do. Okay, so don't be afraid of looking at something and going, I can't do this, it's really hard, it's really hard. That's really good. Those of you that I know, if I'm not pushing you to the point where actually you're having to really think, finding things difficult, maybe coming back and having a look later with a fresh perspective, if I'm not pushing you that hard, I'm not doing my job. So, what I want to have a look at then is we need to be able to write this as a chemical equation. So we've got the full equation here. What I'm going to write now is the half equation for this. And half equations only show, change colour again, let's go to purple. Half equations only show the electron transfers. So you'll notice when I write these half equations out, I'm not going to include potassium, because potassium doesn't change charge. It's a spectator ion. It doesn't appear in the half equations. It only appears in the full equations. Okay? So what we're going to have a look at then is chlorine itself, and I'm going to put chlorine molecule down, is going to turn into chloride ions. So, yeah, I did put the charge in there. Chloride ions. And it's going to do that by gaining an electron. Now, we know that things have to be balanced, and we're going to look at balancing equations a lot more as we go through. So to balance it, if I've got 2 chlorine atoms, I must have 2 electrons. Okay? If I look at my bromide needs to lose its negative charge, so it's going to lose an electron on each of the atoms. Remember, it's diatomic, so I've got to write it as Br2. So it's going to lose that electron. So let me just balance this up. So this is my half equations. If, and I really don't like writing it this way, as a chemist it makes me cringe, but at GCSE you can get away with it. If you're struggling with writing it this way, you can also write it like this. So you can also write that bromide, take away 2 electrons, turns into bromine. Remember, these two are exactly the same thing. If you think back to your maths lessons, if I was to add 2 electrons to both sides of this now, I would go from this equation to this one. So they should mean the same thing. This is better. This you can get away with in a push if this hurts your head too much. Okay. As a chemist, I prefer this one, and it's what you'd be expected to do at college and university. But actually, if you can't get your head around this, go for this one. It's absolutely fine. I'll try to just ignore it for the moment. Now, remember we wrote down that oxidation is the loss of electrons. Bromine is losing electrons. So we can say that bromine is being oxidized. So we've got oxidation happening here. Reduction is gain. So chlorine is being reduced because it's gaining electrons. Okay? So let me just talk through that again, just so you've got your head around what's going on. We have a displacement reaction where chlorine is displacing bromide from potassium. We are forming bromine, and we are forming a chloride ion. So we have a solution, and if I was to put my state symbols in here, I've got a solution of potassium chloride. In terms of what's happening for the electrons, the chlorine is gaining an electron from bromine to form a chloride ion. Because the bromide is losing that electron, it's forming bromine. And we can show that with half equations, where chlorine gains electrons. So it's 2 atoms, so I need 2 electrons to form 2 ions. And if you go back up to the full equation, you'll notice this should also balance out here. I've got 2 ions here because I've got 2 atoms here. Bromide, and I've got 2 of them, is gaining an electron, is losing an electron each to form bromine molecule. Now, you can test yourself with any of these, and if you want to have a go at some, and then email them through to me later on to have a look and check you're working out, that's absolutely fine. But we can do some reactions, so we could choose to do, let's do bromine plus lithium iodide goes to iodine and lithium bromide. We could have a look at this, and we could do fluorine plus sodium bromide, and I'll let you balance that one as well. We could also have a look at chlorine plus, and let's make it slightly trickier, we could do magnesium iodide, and we could see what comes out with that one as well. And I'll do one more. Let's do bromine plus aluminium iodide. Okay, I'm going to leave them there as a bit of an exercise, and I'll email this. I'll obviously drop this onto Google Classroom. Have a go at, if you want to sort of test yourself and see what your understanding is. Have a go at those ones. Work out what the products are, balance it, and then have a go at doing the half equations. If you want to do these sort of diagrams as well, absolutely fine. If you want to do it handwritten on paper, take a quick photograph and email it through that way. Again, not a problem. I'm more than happy to have a look, and we can go through that there. If I get lots of misconceptions, I'm more than happy to do a quick 10-minute video later on, and I'll just put some of those misconceptions correct, because actually it's quite nice now to start pushing ourselves to some of the really high-level stuff when we've got the time to play around at home with it. Okay, so hopefully that's been useful today, and hopefully I've sort of really stretched you in that last part. We are going to be coming back to that again. We're going to be looking at it quite a few times, so really don't worry if you're looking at that going, that's really hard. That just means actually that's really good, because that sort of tests you a bit more. If you are struggling with it though, ask me questions, or we can go through it a bit more when we get back to school. Okay, either way, have a great weekend. I will see you on Monday. Remember, next week's Seneca work is going to be on chemistry 2. So if you want to do some research around it, look at some of the YouTube videos, look on Bite Size, look on Oak National Academy. Anything you want to do, look in the revision guides. So anything you want to do on that, feel free. And then we'll pick up this on Monday. Have a great weekend. Hope everybody's well. Looking forward to seeing you soon. Take care.